Hey, so hello everybody. I'm Richard Southwell. I'm a researcher and I want to talk to you a bit about a project which I've been doing. So it's a project about complex networks. And so right here on the screen, I'm showing you an example of a complex network. You see we have lots of dots that we usually call vertices, and they're connected by some lines which are called edges. And so we have this kind of visually pleasing, intricate shape here, and this is just a representation of this particular graph. There's actually many different representations. You see, one of the wonderful things I like about graphs is that they're so simple. All that really matters is how these different dots are connected by lines. I mean, children do dot to dots, and really graph theory is pretty much exactly that. It's not really very much more sophisticated in some sense. So on one hand, graph theory is very, very simple, but on the other hand, it's incredibly complicated and hard to understand and important. Okay, so why is it complicated? Well, because the number of different graphs that there are grows exponentially with the number of vertices, and it's incredibly difficult for humans to understand things like a large complex graph structure like the one I'm rotating on the screen. Okay. Why is graph theory important, or networks equivalently? Why are networks important? Well, because networks are all around us. I would say that networks are all around us outside and inside. I mean, we can be considered to be parts of networks, social networks, our websites, our vertices within the internet, within the web, our selves are vertices within the global social network. So certainly in some sense we are part of networks, but also in another sense networks are part of us. Our regulatory systems, our circulatory systems, the protein-protein interaction networks defining our organisms, these are all essentially network structures. And so in a way we're part of graphs and we're made out of graphs. And there's also some very interesting theories of fundamental physics which propose that the entire universe is just a giant network structure. And if you look at some of the recent work on the cosmic web, you can see that there's certainly some indications that the very large-scale structure of the universe does look very much like a graph structure. Okay then, so that's the motivation part done. What I actually want to talk about are some extremely simple models for the growth of complex networks. Okay, so in fact all these networks which I'm showing you here, these were produced by incredibly simple models. They're very easy to understand how they work, and they're very trivial to sort of simulate on a computer. You see, people have understood for quite a few years that complex networks are important to understand, and there have been many models which people have created. But the thing is that most of those models are based around random numbers. The original sort of graph model, if you like, was the Erdos-Renyi model, which is basically that you throw down a load of dots and then you randomly connect the dots with lines. So for example, you say that any pair of dots will be connected by a line with a probability 0.5 or something like that. So a model like that can obviously produce complex networks because essentially you're just randomly sampling from the space of all networks. It's kind of like throwing out a net and picking out some randomly chosen network structure. So obviously a model like that can produce complex networks, but it doesn't really give you any idea of where complexity comes from. Now, In more recent years, there have been various different kinds of probabilistic models of network growth. The Watts-Strogatz small world model, the Barabasi-Albert preferential attachment model. You can find a lot of literature about these kind of things. I mean, they're very well known. And basically, these are other kinds of probabilistic network growth models, and they're particularly relevant because they reproduce effects which are observed in many different kinds of complex networks. But the thing is that, again, as models of complex networks, I find these models in some sense unsatisfactory because they're based on randomness. I mean, why do these models produce complex networks? Well, it's because basically underneath the model is a load of random numbers. Randomness is artificially injected into the model, and therefore the model offers no real explanation as to where complexity arises. And that's why I became especially interested in how complex networks can be produced by simple deterministic rules. I want to have systems with very, very simple rules where the complexity arises naturally, not as a kind of artificially injected component, but as a kind of intrinsic feature of the models, which ultimately was unexpected. Okay then, so now I'd actually like to introduce these models for you. So the idea is that we have a network. Actually, we have a special kind of network, like this cube shown here, where every vertex has 3 edges that are touching it, that are incident upon it. And there is 1 red edge, 1 blue edge, and 1 green edge. Okay, so we have this funny kind of network where every vertex has 3 connections, and those connections are coloured red, blue, and green. For those of you that know about such things, networks like this are called Tate-coloured graphs, but the terminology is not really important. What's important is that these are dynamical systems, okay? So basically, we have this special vertex here, which we call a yellow, and we call this the writer. And the idea behind these systems is that the network changes because this writer moves around and it kind of rewrites pieces of network structure as it goes. More particularly, different kinds of structural modifications are made to the network in response to its surroundings according to these little rules here shown at the top. And so, to evolve this system through time, we keep looking at the surroundings of the writer, and then, depending on what those surroundings look like, we apply one of these different operations. And these operations involve potentially modifying the network structure and moving the writer. So, let's just have a look at how this particularly simple example works. Okay, so this is the initial network. And now, to determine the network on the next time step, let's look at the writer. We'll look at the surroundings of the writer, and we'll notice that there's actually no edges linking the writer's neighbours. Okay, so that means that the surroundings of the writer look like this. And so we're going to apply this rewrite rule here on the first time step. So now we get this network. And what we've done here is we've replaced the writer vertex with a triangle and moved the writer along this blue edge. Okay, that leads to this structure here, which is the network on the next time step. And now, to evolve a system, we just do this kind of operation again and again and again. So, once again, we look at the surroundings of the writer, and we decide which rewrite rule should be applied, and it's this one here. So, let's apply it, replacing the writer's position with a triangle, and then moving it along a blue edge. Okay, so what about now? What are we going to do now? Well, now the surroundings of the writer are a bit different because the writer is actually part of a triangle. And so, in fact, this is the relevant rewrite rule because there is a blue edge linking the writer's neighbours, see? And so now, according to this system, we're going to just apply this rewrite rule here, which just involves moving the writer along a red edge without modifying the network structure at all. And so this is the network on the next time step. Alright, so now let's just apply these rules again. Which rule applies this time? This rule does, because there's a green edge linking the writer's neighbours. But what does this rule say? It says don't change anything. And so, in fact, we've now reached a fixed point. Because according to this rule here, the writer isn't going to move anymore, and the network isn't going to change anymore. And so this is really quite a simple system which has reached a fixed point. Now, I know this particular kind of behaviour is rather boring, really, but I wanted to use a simple example to introduce these models to you. And I'm going to show you that just by changing these rules ever so slightly, we can really make immensely complex behaviour.
Okay then, so before I get into the details of this project, I'd just like to make a couple of acknowledgements about people whose work really inspired this project. So firstly, Stephen Wolfram. His book, A New Kind of Science, has really inspired a lot of the work that I've done over the years. I think it's a very wonderful book, very original and very creative and very insightful. Basically, in this book, Stephen Wolfram promotes the science of exploring the dynamics of simple programs. And basically, the fundamental fact behind A New Kind of Science is that very simple programs can produce immensely complex dynamics, and that by taking a kind of experimental approach and doing things like just making pictures of the dynamics of large numbers of simple programs, one can find all kinds of fascinating phenomena, and those shed insights into lots of other systems in the natural world and in mathematics. And so, really, this is a very good book, and the project which I've done can really be considered as a part of this new science for simple programs. So I'm really taking this kind of approach which Stephen Wolfram pioneered of using simulations and visualization to elucidate the dynamics of these simple programs. And another person whose work really inspired this work that I've done is Tommaso Bolognesi. He wrote a paper about planar trinet automata, and basically the systems which he considers in that paper are very similar to the ones that I'm discussing here. The idea that you have a writer which moves around in a network, applying deterministic local rewrite rules, is really very similar to what I'm looking at here. And, so in a way, as far as the concept goes, I'm really indebted to him. Although the systems I talk about are pretty different to what he talks about. And, in a way, I'd say that the systems I'm looking at are kind of simpler and maybe a bit easier to visualize as well. So, this is a very inspiring piece of work, and I urge anyone to check out Tommaso Bolognesi's stuff. It's very good. Okay then, so now let me start talking about what I actually did. I chose a space of rules, a space of systems to look at, and I looked at every single one and I classified the kinds of behaviour which I saw. So what's the rule space? What's the space of systems? Well, there are 3,888 different systems that I looked at, and this is a kind of illustration of the rule space here, of the system space. So basically each of the systems I look at are specified by 4 different rewrite operations. One for these kind of surroundings, one for these kind, one for the one for this kind, one for this kind, one for this kind, and one for this kind. So by specifying how the writer moves and what kind of structural modifications are made in response to each of those different kinds of surroundings, we specify a particular rule. And so we looked at rules where these kind of operations are allowed here. So whenever we have no edges linking the writer's neighbours, we force the writer to be replaced with a triangle, and we allow the writer to move up to 2 coloured links away. So these are the different possible rewrite operations which we allow. When there is a red edge linking the writer's neighbours, we allow these different 18 possible rewrite operations here. And these are all the ones which involve possible triangle replacement and movement of the writer over up to 2 coloured links. Similarly, when there is a blue edge linking the writer's neighbours, we allow each of these 18 possible rewrite operations. One restriction that we make is that when there is a green edge linking the writer's neighbours, we just force the system to be fixed. Okay? So basically, this makes 3,888 different rules because there's 12 things like this, 18 things like this, and 18 things like this. And, you know, we have this arithmetic here. But essentially, I just want to tell you about this rule space which we studied because it's kind of important, you know. The rules which I'm going to discuss are very simple. They only involve potential triangle replacements and movement of the writer over 1 or 2 coloured links. So really the systems are extremely simple, and the rule space is really quite small. And so this has a couple of benefits. Firstly, it allows us to really find minimalistic rules which produce certain kinds of behaviour, like highly complex behaviour. And secondly, having a very small rule space like this really allows us to do a complete classification of the dynamics of the rules, or at the very least we can just look at the dynamics produced by every rule and really gain a kind of global understanding about what's possible with the very simplest kinds of systems. And another sort of major insight from a new kind of science is that really often the kinds of phenomena which you observe by looking at very simple programs are repeated many, many times when you look at more complex programs. So if we look at more elaborate kinds of network rewrite systems, I would expect we'll see very similar behaviour occurring.
So that's a little bit about the rule space. Now I want to actually start talking about really the project. So I've given you the motivation, the model definitions, description of the rule space. Okay, so what we actually did in this project, or what I did, I suppose I'm the main worker on it, was to go through lots of all these different 3,888 different rules and to look at what kind of behaviour they can produce. And so, as I've already said and shown, one kind of behaviour is fixed points. So what about the fixed points? Well, it turns out that in fact a lot of the different rules produce fixed points, and that's actually really just a consequence of the fact that all our rules involve this kind of thing here, where wherever we run into surroundings that look like this, our system ends up being fixed. And so out of all our 3,888 different rules, we have that 2,918 of them end in fixed points, okay, when we evolve them. So for each of our rules in this experiment, we always start from this cube network here, because it's a nice, simple starting point. And as I say, in about 75% of our rules, our systems, they reach a fixed point. And so why do so many of our systems reach a fixed point? Well, it's because whenever each of our rules are such that whenever we have this kind of surroundings, the system becomes fixed. And in fact, 2,562 of those rules which reach fixed points for exactly this reason, that these kind of surroundings are realized and then the system halts. Okay? Alright, so we know that lots of our systems reach fixed points, but how long does it take? In that example I just showed you, a fixed point was reached very quickly. But what about this system? We can ask, for example, what's the longest amount of time it can take to reach a fixed point? Or what's the largest kind of fixed structure which can be created? Which ends up being... So, let's have a look at this system evolving. Okay? You'll notice that the network structure is changing and it's looking quite complicated. And this is because I'm actually using a different kind of graph drawing technique here. This is actually a graph drawing algorithm which I developed myself. Because the other kind of planar representation I was showing before just isn't always possible, or it isn't always easy to do with these kind of systems. Okay, so what's going on with this rule? Well, you can see that quite a complicated network is being produced. I mean, we're still obviously following deterministic rules. These rules are a little bit more complicated now. For example, here, we ought to be applying this kind of rule here. So we'll replace the thing with a triangle, and then move across a blue and a green edge. So we want to be going over there. Yeah, and we're keeping following deterministic rules, but we're now getting a more intricate kind of network out. And so what's going to happen? Is the thing going to keep bubbling around kind of randomly? Or, well, in fact, we end up reaching a fixed point right here. Okay? So you can verify that this is a fixed point. You can see that the writer is part of a triangle here, if you've got good eyesight. And actually the writer's surroundings look like this. And so according to this rule, a fixed point has been reached. Okay? And so, in fact, out of all the 3,888 rules we considered, this one here, specified by these 4 little pictures at the top here, this rule is the one which produces the largest fixed structure when evolved from a cube. So this network structure here, this has 56 vertices. Okay? So, I mean, it's not mind-blowing. It's not a huge structure, but I think it's kind of interesting that this thing can evolve for 26 time steps from such a simple initial condition and then suddenly just halts. It's a very abrupt change in the form of behaviour. Okay, so I'm regarding a rule to have reached a fixed point when there comes a time after which the network structure is never ever going to change. So for these kind of systems which we're looking at, there's actually kind of 2 different types of fixed points that can occur. There's the simple kind of fixed points where the writer stops moving and the network stops changing. And then there's also a kind of slightly more intricate kind of fixed point where the network goes fixed, but the writer keeps moving around. Okay? And so I'll show you an example of the second type. So this network here, this actually takes the longest of any of our rules to reach a fixed point. It takes 34 updates, and eventually there comes a time when the network structure becomes fixed, but the writer continues to hop around in a kind of period 2 orbit. And that's just because this rule just keeps getting applied over and over again. Okay, so now I've shown you the network, the biggest fixed network that gets produced, and the system which takes the longest amount of time to reach a fixed point. So now it's time to go on to a different kind of behaviour. Okay, so the next most complicated type of behaviour which these rules can produce, is what I like to call repetitive growth. And so repetitive growth is characterized by the feature that the network continues to grow while the writer's surroundings change periodically. And why this happens is because the writer sort of gets trapped within a particular piece of a network within which the surroundings that it produces induce it to keep making surroundings in a similar way. That maybe sounds a little cryptic. An example should let you know what I mean. Let's have a look at this rule here. So we apply this rule, and then according to our thing, this type of operation should be applied. So there we go. And now look, the writer's surroundings are once again of this kind of blue triangle type. Okay, so again we're going to apply this rule. Now what's happening? Well, again, the writer's surroundings are of this type, because actually the way this rule works is that it ends up that the writer's surroundings are of this type again. And so we can see that the writer is going to be kind of eternally trapped into having this same kind of surroundings sort of forever. And what this actually leads to is this sort of long ladder-like structure. So this is what I call period 1 repetitive growth, because the writer's surroundings are changing with period 1. You know, I shouldn't go into too many technical details during this presentation, so you can check out the paper, which is linked to at the bottom, if you want more details. There's a kind of rigorous mathematical definition of this sort of repetitive growth. Anyway, the point is that you can actually have higher period repetitive growth as well. Okay, so now I'll show you a slightly more elaborate rule which produces higher period repetitive growth. Okay, it's not really much more complicated, but here we are. So let me just show you it evolving. For the first 10 time steps or so, the way the writer moves looks like it's quite unpredictable. But then we get this time when we settle into this repetitive growth. Okay, so you see here this rule should be applied because the writer has this red edge linking its neighbours. And so what happens when this rule is applied? Well, the writer is actually going to move over here, and you can see that in fact the writer is again going to be of this type, and again it's going to be facing a triangle. And so in a sense, if you imagine looking at the writer and looking at all the vertices within a certain distance of a writer, in this case a distance of 2, as in all the vertices within 2 links, then the fact is that that kind of structure there is actually remaining fixed. And that's kind of why this repetitive growth is ensuing. Okay, so let's actually evolve the thing. You see that basically the writer is just hopping between these 2 vertices from this point on. And so when you draw the graph structure like this, it gives the effect that there's this kind of large handle being growing out, with this kind of ladder structure. And it's really quite a simple kind of behaviour. But basically, it occurs because the writer is kind of trapped within this place where its surroundings are changing periodically. And if one looks at all the different rules, after fixed points, repetitive growth is the next most common type of behaviour which is observed. In fact, 840 of the rules end up producing repetitive growth. Obviously, when a rule is producing repetitive growth, it's really quite easy to describe its dynamics. So we wouldn't really say that repetitive growth is a very complicated type of behaviour, because once you've seen how it goes, it just repeats, obviously. It's kind of a definition. Anyway, so 840 of the rules make repetitive growth. 836 of those have this really quite simple behaviour, where the repetitive growth settles in quite quickly, within less than 40 time steps, and it doesn't have a very high period. It has a period of, say, 12 or less in each of those cases. So the majority of the rules which exhibit repetitive growth, which we found, really do it in quite a simple way. However, there are 4 little beasties, 4 little rules, which actually produce much more complicated types of behaviour. And that's what I want to talk about next. Okay then, so now we're getting to the good stuff. This is a rule which also exhibits repetitive growth. You remember? I said there was 836 that make simple repetitive growth. This one, well, it ain't simple. Let me just show you it evolving for the first 300 time steps. So, as you can see, the system is not quickly settling into anything like repetitive growth. I mean, just watch the way the writer is moving around. See if you can guess which way the writer is going to go, or what's going to happen. Well, I'll wager money that you can't guess how this system's evolving, unless you've watched this video before. And, the writer seems to be moving around in a fairly random way. It doesn't seem to be going around in circles or staying in the same place in the network. And the network looks fairly self-similar, but again, it's difficult to predict how exactly it's been produced. And so, in fact, this system, I would say, has a kind of complex behaviour, at least initially, because the way the writer moves is very hard to predict. It certainly hasn't settled into any easily decidable kind of behaviour. Okay, let's just speed it up now. So, yes. For the first 300 time steps, the way this system evolves really does look quite unpredictable. And you can see that the network being produced is really quite elaborate. However, it turns out, quite interestingly, that the behaviour doesn't stay this way forever. So, here's a picture where I've tried to illustrate a few things about the dynamics of this system. Firstly, here, this is just a snapshot of the thing evolving, and and we've got these yellow arrows here, which are just showing the kind of track of where the writer has gone. Okay. So now look at over here. Here we have time on the x-axis, and the y-axis here is the position of the writer. Now, you might be thinking here, what do you mean? How can you associate the position of a writer with a number? Well, obviously I used a computer program to generate these networks, and when you store a graph in a computer, you generally have to label the vertices with different numbers, vertex 1, vertex 2, etc. And so, if you have a graph which is evolving, like these systems do, you have to think of some kind of scheme some kind of way to index your vertices. Well, the scheme I used was that when a vertex is replaced with a triangle, we'll give the vertex which has the red external link of that triangle the same index as its parent, the thing it replaced, whereas the other two vertices, the ones with the blue and green external edges, they get indexes L plus 1 and L plus 2, where L is the number of vertices in the structure before this triangle replacement operation. So this is a fairly simple kind of indexing scheme. Basically, when new vertices are produced, they just get indices, which are like the next highest indices up. And it turns out that this is actually very useful, because if one just looks at how the index of the vertex which the writer is on changes with time, then that plot is very revealing. For example, here, just by looking at this plot and maybe doing a bit of statistical analysis, we find that the writer seems to be moving in a kind of pseudo-random way for the first 4,994 time steps. That would be this kind of area over here. And then suddenly, the writer starts moving it with repetitive growth. But the repetitive growth is not fast, it's not low period like before. Now this repetitive growth has period 454, so it's quite remarkable. The system does produce repetitive growth, and that can be seen more clearly by looking at this snapshot here, which shows the network structure on time step 7000. And so you can see that repetitive growth is occurring because of this kind of handle of repetitive structure which is getting created here at the right. This is really a massive network with thousands of vertices, and it's remarkable how much structure is actually produced before we get this repetitive growth kicking in. Actually, I think it's fairly interesting. I would draw a kind of parallel here with the development of plants, because I mean, if you drop a seed in the ground, it'll start by complicating the structure immediately around the seed, a bit like these things complicate the structure around the initial cube. And it'll do that in a fairly intricate way. And then the plants will grow out this long kind of serially repeating one-dimensional style structure, which is the stalk of the plant. Well, in a similar way, after this rule has complicated the structure around the initial cube, it grows out this large kind of one-dimensional handle here. So there's some kind of conceptual similarity between this and the development process of plants. So there are actually 4 rules which produce repetitive growth in a similar kind of way. And you know, this kind of long transient repetitive growth, which is really a sort of complex behaviour. And one of the rules I've just shown you, and there's another rule which is symmetrically equivalent to it. If you swap around the roles of colours red and green, red and blue, you get the same summing equivalent. And so then there are 2 other rules, and those also generate high period repetitive growth eventually. So here's a video of one of those rules evolving. So this is the other one which eventually generates repetitive growth. But as you can see, it actually produces a very complex structure, and once again the writer movement seems quite difficult to predict. I think this system's actually maybe a bit more complicated than the one before in some sense. It has a longer transient. In this case, the transient time within which the writer moves around randomly is shown here. This lasts for 17,615 time steps. So honestly, I had to run this thing for a long time to figure out that it did actually eventually become repetitive. And when it does become repetitive, it settles into a 1,355 period repetitive growth. So, even when the thing does become repetitive, it takes a real long time for it to repeat. Anyway, the fact that it does become repetitive means ultimately its behaviour is predictable, but it really does produce some very, very complicated network structure in the meantime. This is a snapshot of a network produced. I think this is on time step 1000. So it's very complicated. And just to prove to you about the repetitive growth, here's another plot of the index of the writer over time. And you can see that eventually it becomes repetitive. But look at these time values. It takes a long, long time for a thing to become repetitive.
Okay then, so I said there was 4 of these rules which have the long period, long transient repetitive growth. And so actually the 4th rule is symmetrically equivalent to the last rule I've just shown you under a red-blue swap. So really there's 836 of these rules which have this kind of very simple repetitive behaviour, and then there's these other 4 rules which have this very complicated behaviour which eventually becomes repetitive. But if you disregard symmetry and only take one copy of each fundamentally different rule, you find that there are only actually 2 of these rules which are initially chaotic and then eventually repetitive. Now, I want to talk about the 3rd and final class of rules. So I've talked about rules which go to fixed points, rules which eventually make fixed networks, and I've talked about rules which generate repetitive growth. In fact, the vast majority of the rules are of one of these 2 types. But I'm going to now define the 3rd type of behaviour, and I'm going to call it elaborate growth. Now, basically, I don't really need to say what elaborate growth is, because we can just think of it as other, okay? It's where all the other rules, which we haven't classified so far, lie. Because we'll say that if a behaviour is not fixed or not repetitive, then it's automatically elaborate. That's a little bit of a cheat, and in fact, this sort of world of network rewrite systems is a lot simpler than that. And so it turns out that, in fact, these rules which generate elaborate growth do have certain kinds of behavioural characteristics. So I can't really give you a sort of definition, because the problem with these systems is that without really rigorous analysis, it's quite difficult to be absolutely sure you know what's going on. So I can't really give you a solid definition of what happens in elaborate growth, but I'll tell you some of the features which I've observed. Okay? So, firstly, obviously elaborate growth involves the network growing forever. I mean, the way these systems are defined, the way our 3,888 rules are, is that the only way a network can be modified is by replacement of a vertex of a triangle. And so what that means is that the number of vertices it can never decrease with time. And so either the system reaches a fixed point or it grows forever. And so these elaborate growth systems grow forever. And what else? Well, the thing is that the writer tends to move on a kind of one-dimensional track. What do I mean? I mean that from any particular point, one can look at the future or previous movement of a writer, and one can see that it forms a 1D track that's that's predictable, really. So the overall behaviour of these rules of elaborate growth might not be predictable, but the writer movements tends to be confined to a one-dimensional track, and that often means that these systems of elaborate growth tend to be equivalent to string rewrite systems, like Lindemeyer systems. Another thing about them is that these systems often lead to self-similarity. And I say this slightly cautiously, because the vast majority of these rules certainly do lead to self-similarity, but there is one which stands out as particularly complicated. So remember, we've got lots of rules here, and given the ability of these kind of systems to surprise one, it's really quite reckless to try and make general assumptions without rigorous checking. But the problem is here that rigorous checking is almost impossible. I mean, I think these systems with elaborate growth are really kind of equivalent. Conceptually, they're sort of similar to the cellular automata, which produce nested patterns. Okay, so what about the class of cellular automata which produce nested or fractal patterns? Well, that class of cellular automata is not very well defined, because firstly, what is a nested or fractal pattern? That takes some defining. And secondly, yes, maybe 90% of cellular automata can be easily checked, can be easily sorted into. You can easily decide whether it's producing a nested pattern or whether it's not. But then there'll be some borderline cases where the pattern looks kind of nested, but there's also elements of complexity there, and perhaps the pattern is in fact not nested. And without really rigorous analysis, it's very difficult to sort, because that's actually not a very good criteria for sorting out these different automata. Anyway, what about this system here? This is perhaps the simplest system with elaborate growth. So let me just show you it running. Okay, so you should notice that the writer is actually moving around and around. Let me just pause it. So notice a couple of things. Firstly, the writer is moving around and around in circles. Okay. Now think about how the writer is actually moving. To do this, let's actually just have a look at our rules. So what happens in this case here, where the writer is not part of a triangle? Well, in this case, our rule says that the writer should move across a red edge and a blue edge, and the writer's previous position should be replaced with a triangle. Okay? And what happens in this case here, where the writer is part of a triangle and it has a blue external edge? Well, in this case, our rule says that the writer should move across a red edge and a blue edge, and then the writer's previous position should be replaced with a triangle. And so we can summarize the rules behind this system as follows. The rules are basically that if there are no edges linking the writer's neighbours, or if there is one edge linking the writer's neighbours, which is blue, then replace the writer's position with a triangle, and then move the writer across a red edge and a blue edge. Otherwise, the system is fixed. The system has reached a fixed point. So, really, the system is quite simple as far as the rules go, in that we can describe the rules in a couple of sentences like that. Now, the most important thing to notice here is that every time the writer moves, its movement can be expressed as a combination of traversals of red edges and blue edges. Even simpler, really. Every time it moves, it just basically moves across a red edge and then a blue edge. Why is that important? Well, because we can see that the motion can be described only as a combination of traversals of edges of only two different colours. And what that means is that essentially the writer is confined to a one-dimensional track. Okay, again, I think I'm being a bit cryptic here. So just think about this. These kind of networks, which I've described, have this feature that every vertex has a red edge, a blue edge, and a green edge incident upon it, and that's all. And so, think about any kind of graph like that. Pick any vertex you like. Now, from that vertex, move along a red edge, and then a blue edge, and then a red edge, and then a blue edge, and then a red edge, and then a blue edge. And just keep doing that. Suppose the graph is finite, it has a finite number of vertices. Well then, eventually, you've got to come back to one of the vertices that you've already started from, because there's only a finite number of vertices, so you can't keep visiting new vertices forever. So eventually you've got to return to one of the vertices you've already walked across. But in fact, you must return to your starting point, because you can't return to any of the other vertices that you travel to intermediately, because for each of those vertices you've already traversed a red edge and a blue edge incident upon them. And so if you return to such a vertex, you'll have broken this rule, because you'll have found that that vertex actually has two edges of the same colour touching it. So that's kind of a proof by contradiction, and what it shows is that if you keep traversing a red edge and then a blue edge and then a red edge and then a blue edge, etc., you eventually come back to your starting point. In other words, each vertex lies within a unique cycle of edges of alternating colour between red and blue. And so what that means in this case here, for example, is that the writer is actually confined to a one-dimensional track. See? Here's the writer, and then it can go across a red edge, a blue edge, a red edge, a blue edge. I mean, it's hard to see because of the way this thing's drawn, but if we keep following this cycle, we end up getting back to where we started from. It's actually easier to see if we look closer off to the beginning, so let's just... Right, here we are. Red, blue, 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 red, blue. And there we are. This is the alternating cycle. Now this writer is going to continue moving around this alternating cycle, and the structural modifications it makes are just going to lengthen this cycle. I mean, just watch. See how this cycle gets longer as the thing moves around. Okay. So that's the first thing. In this case, you can really prove that the writer is confined to a one-dimensional track, and that it's moving round and round in the same direction. As this network is drawn, the writer is constantly moving around clockwise around this cycle, and in fact, the cycle's getting twice as long every time the writer goes around it. So that's the first thing. Second thing is we actually have self-similarity. Okay. See if I'm good enough at stopping this video at the right times to show you. Right. So look at this network here. Okay. Now look at the network after the next traversal. A bit too far. Let's see if I can stop it at the right time. Right. This is the network after the next rotation. And you can see that now we've got two of these little triangles here. Notice that what we've actually done here is we've got the original triangle, and then we essentially replace the corners of that triangle, which had the blue and the red external edges, with separate triangles. And in fact, I claim that every single traversal does that operation. So that the next traversal of this circuit is going to have the effect of replacing every triangle, each of the four triangles in this picture, with one of these funny shapes here. So if you want it a bit more technically, each traversal that the writer makes will replace every vertex of a triangle which has a blue or a red external edge with another triangle. So let's see if I can stop it again. Okay, so the writer's just gone through this top left triangle here. And now notice we've got another one of these patterns here, which looks similar to what we just had. And we've got another one here. And
Well, I'm just going to let it run. Hopefully you can see the self-similarity occurring. Anyway, so it turns out that in this case, one can really pretty fully understand the dynamics of a system. In fact, one can get a completely rigorous description of the dynamics of this system, which is really quite nice. So I'll show you that in a second. I'll just let this thing run. Just want to say actually that really these kind of systems, for these kind of systems, visualization is key. I mean, these systems running on graphs do have quite a good appeal, have a great appeal because the networks themselves, there's no specification of how the network should be laid out in space. And so in a way that makes these systems quite fundamental. For example, if you think about physics, you know, the most fundamental theory of physics, I believe, is not going to involve exactly how you... It's not going to involve an intrinsic notion of space. I think the idea of space and the idea of a kind of rigid frame where all the action happens is a kind of byproduct of the most fundamental laws of physics. And so, really what I'm trying to say is that systems like cellular automata or differential equations or things like that, which rely on rigid space to be set out before you start, are not as fundamental as they could be, since ideas of space can emerge from simpler systems. And graph-based, adaptive graph-based systems are simpler because all they involve is a network, and the network can be drawn in multiple ways. So in that sense, and in the sense that all kinds of different types of space can be generated, adaptive graphs are very appealing models to study. The problem with them is that it's very hard to analyse them in general because of exactly the fact that there are so many different ways you can visualise them. There's so many ways to draw networks, and honestly, if you have a look at a giant network showing the internet or something, you have to draw it very, very carefully in order to actually be able to learn much from looking at the picture. Often these things just look like giant messes of connections, and it's very hard to understand what's going on. And so finding a decent visualization method is key. And actually the majority of the time I took on this project was really about finding ways to visualize these different systems, and that can be quite challenging from a kind of programming point of view. Anyway, let's have a look at this now. See, this is basically the same system I just shown you, but what I'm trying to do here is illustrate the kind of one-dimensional nature of this system. And so, basically every row of this picture here shows the network on a different stage. So this is the initial cube network here. This is the network on the next time step, and the next time step, and the next time step, etc. Now, I haven't shown the entire network on any particular row. I've only shown what I call the relevant parts of the network. Perhaps if I go back to the video, I can show this a bit more clearly. Okay. So obviously, one can sort of lay out this graph however one wants. And I've already shown you how the writer is confined to this red-blue cycle. And so the idea is that we can actually just visualize that as a one-dimensional thing. But there's a couple of issues here I want to point out. Firstly, this outer face of the network is completely irrelevant. I mean, the writer never touches it. And in fact, even these edges here, which kind of link the outer face into the inner face, they don't really have any relevance to the dynamics. So we might as well just cut all this stuff out.
that's not relevant. And secondly, these edges, such as this one here and this one here, which are not part of triangles, also end up having no influence at all on the dynamics. Why? Well, because all that matters as far as how the writer moves is which vertices are part of triangles and which vertices are not. And these edges are not part of triangles, and we don't make anything become part of triangles. And since everything only expands, these things are always going to never be part of triangles. So we might as well just erase every green edge which is not part of a triangle. And then we get this kind of ultimately boiled down kind of network, which only really holds the fundamental things that we need to think about for the dynamics. And each row of this system here it shows exactly that. It just shows the red edges and the blue edges of the alternating cycle that the writer's on, together with the green edges which form parts of triangles. And as I say, each successive row of this picture just shows the relevant parts of a network evolving over subsequent time steps. Now you can see from this that the way the writer is moving is very simple, and the way the network is evolving is very, very simple. And using this kind of reduction to what is essentially a one-dimensional string rewrite system, we can really gain a lot of insight into the system. In particular, we can derive this particular theorem here. And what this basically does is it gives us a kind of characterization of the behaviour of these kind of systems. So what does this theorem say? Well, it says that if we have a look at the network obtained, we're interested in the form of the network obtained by evolving this system for t time steps. So let's just have another look. That's time step 0, that's time step 1, that's time step 2, okay? So have a look at this, oops. Right, this is a network on time step 2. After 2 updates from the initial queue. And what this theorem says is that for each n greater than or equal to 2, we can find the network on time step 2 to the n plus 1 minus 2 by taking the network at time step 2 to the n minus 2 and then just looking at each triangle in the system and replacing the vertex with the blue external edge and the vertex with the red external edge with triangles. So essentially, to find the network on the next special time step here, we're just applying this operation globally. Why does this result hold true? Well, let's just have a quick look at the dynamics again. Basically, every rotation that the writer makes corresponds to one of these types of rewrite operations. And one can prove this by looking at the one-dimensional kind of string rewrite system that I just showed you. In fact, one can actually use this result to give a more or less complete description of the dynamics of these systems. And it's actually quite interesting because there's some nice relations between the kind of network structure you get from this and some pretty interesting integer sequences. Okay, so that was a little bit about what is perhaps the simplest rule with elaborate growth. In fact, there are 130 different rules with elaborate growth, and they can really be organised into 2 different classes. Rules with what I call cyclic writer movement, like the one that I just showed you, and also rules with what I call bouncing writer movement. So, before I go on to bouncing writer movement, let me just show you another example of a rule with cyclic writer movement. Here it is. So it's quite similar to the one before, sort of qualitatively. The writer is rotating around. This time it looks like it's going anti-clockwise as far as the way the network is drawn. And you can see that the pattern it's producing is more intricate, but there still looks like there's quite a lot of self-similarity here. Another important feature is that if you actually have a look at the rules, you can see that once again the writer's movement can always be expressed as a combination of movement over red and blue edges. Here it goes over a red and blue, here it goes over a red and blue, here it goes blue-red, and here it doesn't move at all. So again, we can do this kind of reduction to a one-dimensional string rewrite system. However, there are some important differences in this rule. Basically because the dynamics that this system produces are more complicated than the last system. Let me show you that. Okay, so in each of these systems, the number of vertices is growing approximately linearly over time. And that's pretty easy to see, because every time you replace a vertex with a triangle, you're adding 2 more vertices to the system. And so if there's some kind of regularity in the way that the, in the times that triangle replacement occurs, then you're going to get a linear growth. And so actually, if you look at this system here, if you just plot the number of vertices over time, you see that it's approximately linear. And the best fit, say t is time, the best fit that you can do would be that the number of vertices is 1.38 times the time step plus 7.92. But that's not an exact fit. And in fact, the way the number of vertices is, the way the number of vertices deviates from this best linear fit is really quite complicated, as I've shown by this graph. So this graph shows the number of vertices take away this best linear fit over time. And you can see that the way this best fit deviates from the actual value looks kind of complicated. And so, does this mean that these systems have complex behaviour, in quotes? In fact, no, not in this case. Because in this case, it turns out that one could actually find a rather nice description of the number of vertices in terms of the golden ratio. And so this is our second theorem here. This actually took quite a lot of proving. Basically, it's a formula for the number of vertices at time step t within this network. And this is the formula. So these are floor functions and ceiling functions, and this phi here, this is the golden ratio. 1 plus the square root of 5, all divided by 2. And so there you go. In this case, one can find an exact description. The proof of this essentially boils down to reducing the system to a one-dimensional system, which is kind of like a Fibonacci-style string rewrite system. But the reduction is quite non-trivial. Now I want to show you one more rule with cyclic rate of movement. Another one of these rules belonging to this class of systems with what I call elaborate growth. And I think this one actually stands out because really, out of all the 3,888 rules, this one is pretty much the only one, together with its red-blue reflection. This is the only fundamentally different one which has behaviour which I would say has completely stumped me. Completely unpredictable behaviour, or so it seems. Now in the last case I just showed you, I had that rule based on the golden ratio, and the growth rate looked very complicated, but in fact it turned out not to be that complicated. It turned out that there was a simple formula for it. Maybe the same is true here. I'm not sure. But let me just show you the system evolving. So here's the thing evolving using one of those kind of planar embeddings. And one can see that again the writer on average is going around and round in circles. It takes a couple of back steps, but mostly it's going around in circles. Again, the writer's confined to red-blue edges. And it doesn't look like the pattern which it's producing is that complicated, and maybe it isn't. I'm not sure. But I am sure that the growth rate looks very, very, very non-trivial. So let me just show you that. I mean, again, growth rate is approximately linear, but if one takes the best linear fit, okay, this is the thing running for 10,000 time steps. Now, the best linear fit one can do is that the number of vertices at time step t is 1.31 times t plus 5.45, okay? But if one looks at how the actual number of vertices deviates from this best linear fit, it looks extremely complicated. And as you can see by this curve, in some ways it looks kind of random. So I think this is fairly interesting. And I think this is a sign that there's significant complexity afoot. Now, I am a little bit reluctant to say that this is a completely pseudo-random system, because it does look like there are some regularities here. For example, look at this piece of the curve here. Can I draw a box around it? Okay, it's a bit difficult. Maybe I'll print screen. Put it in paint, that's easy to use. Okay. Right, so if one has a look at this piece of the curve here, then that actually looks pretty similar to this piece of the curve here. And so this kind of tells me that there are some kind of regularities here, and who knows, maybe there is some kind of complicated number theoretic function which gives this curve exactly, or maybe even something quite simple. But as far as I can see, for as long as you can plot this thing, you get this curve which looks very kind of random. And so I'd say this particular rule stands out as the sort of only rule which has significantly complex behaviour which persists forever. Because it really looks like however long you run this system, it just always keeps growing in this complicated way. And the system can be reduced to a one-dimensional string rewrite system, and at some point in the future I intend to roll up my sleeves and see if I can actually describe the dynamics of this system, or perhaps prove that it has some kind of complexity. So that's a fairly interesting project to do in the future. But I think this is one of the benefits of this kind of approach, because I can say with certainty, or almost certainty, that this is really one of the simplest adaptive graph systems with complex behaviour. Okay, so like I said, there are 130 of our 3,888 rules which produce elaborate growth. And in fact, 26 of those rules produce this kind of... 104 of these rules produce this kind of cyclic writer movement based thing. And most of that behaviour is fairly simple. Often those rules tend to be things like reflections of the things I've already talked about. However, 26 of those rules produce this other kind of behaviour that I alluded to before that I call bouncing writer movement. So what's bouncing writer movement? Basically that's where instead of the writer going round and round in circles, the writer kind of goes forwards and backwards along a one-dimensional track. So it's easier to show you by example. Here's a rule with bouncing writer movement. In this case, the writer is confined to the track, which consists of these red and green edges instead of red and blue edges. But watch the writer. You see it keeps bouncing off this piece of the graph here. It doesn't go around in circles. It'll go around to the left and down, and then it bounces off here, and then it goes off in the other direction. and it's going to go around here, and it'll bounce off again and go in the opposite direction. And one can see that it's producing a self-similar pattern once again. So these rules with cyclic writer movement, they also have this property that the writer moves in an effectively one-dimensional way, and it tends to lead to self-similar networks. Okay. So in this particular case, it turns out that once again one can reduce the system to a one-dimensional string rewrite system, and one can also effectively describe the behaviour. And so again we have this feature that with each traversal of the one-dimensional track, the writer effectively performs a global rewrite operation. So in this case, each traversal effectively applies this rule, these rewrite rules, simultaneously wherever possible to every vertex apart from the vertices which are part of the external face of the cube. You should have a look at the technical report of the paper for details. But I mean, if you just look at the network on these different time steps, you can see that effectively you're just applying global rewrite operations to get from one to the other. So there we go. Okay, so that pretty much concludes my discussion of these 3,888 different rules. So just to summarise the classification scheme, we find that there are fixed points of two different types. Fixed points where the writer ends up fixed, and fixed points where the writer ends up moving. And we find that there are rules of repetitive growth of two different types. Repetitive growth with very small periods and short transients, and repetitive growth with extremely long periods and long transients, which effectively corresponds to complex behaviour, something like cellular automata rule 110. And we also find that there are elaborate growth of two different types, cyclic writer movement and bouncing writer movement. So that pretty much concludes our classification of the 3,888 different rules. I'm going to put some documents out there. I'll put links to this description bar, and I'm going to put somewhere on the internet, I'm going to put a full classification of all of these rules, perhaps with some mathematical code that you can use to actually run the things and verify what I'm saying is true. Anyway, remember that these 3,888 rules are really a very, very small sampling of what's possible in these systems. For example, we always stipulated that this fourth part of the rule was always fixed, always led to a fixed point in all the rules I considered. But if we drop that restriction and consider more general rules, we find other types of behaviour. For example, this rule here. Let me run it for you. So just watch the way the writer moves here. It really looks as if the writer's moving in a rather unpredictable way, and the network being produced looks very kind of complicated. And I've run this rule for 500,000 time steps, and unlike the other things that I found before, this thing doesn't seem to settle into repetitive growth. As far as I can tell, the writer keeps moving in a pseudo-random way forever in this system. And who knows, maybe on the billionth time step, the system suddenly starts doing repetitive growth. I mean, it's just very difficult to tell exactly what the long-term behaviour of this system is. Well, so far as I can see, this system just produces complex behaviour forever. And this is a system with 4 active parts, but it's still only involving just triangle replacement. Really very simple kinds of rules. In fact, this is the only rule I've found where the writer seems to move in a very kind of random and unconfined way for as long as I can tell. Okay, so this is one kind of dynamics that one finds if one looks at these more general rules. And then there's various other kinds of behaviour that one can see. Maybe I'll just stop running now. Okay, so here's a plot of the writer position over time for this rule I've just been showing you. And you can see that it looks very complicated. Okay, so one can also consider, of course, more general kinds of rules. For example, here I've got a system which involves this rule here, which involves actually shrinking a triangle to a vertex. And with rules like that, one can see other kinds of behaviour. For example, it's possible that the shape of the network oscillates over time, because it's possible that the number of vertices decreases at a given time step. So one can find extremely large period orbits where the network just keeps changing, kind of like flapping in and out, expanding and contracting. And one can also see things like this. This rule here has a sublinear growth rate. All of the systems I've shown you so far either end up as fixed points, or they tend to have linear, or at least approximately linear growth rates. But here the number of vertices looks like it grows something like the square root of the number of time steps elapsed. Okay, so here's just an example, a very simple example of a system where the network expands and contracts in a periodic fashion. And then one gets more interesting rules like this. Okay, so I want to say something about dimension now. There are a couple of definitions of the dimension of a network. So this is really a kind of an extrapolation from the idea of Euclidean space. Basically, one says, okay, I like thinking in terms of dimension. I like thinking about one-dimensional, two-dimensional, three-dimensional space. So a graph corresponds to space, so I want to associate a graph with a dimension. How do I do that? Well, there's a few different ways to do it. One way is to say, well, in a circle, the number of vertices which are a given distance from a circle grows like pi r. Well, so it's equal to pi r, if r is the radius. And in two-dimensional space, the number of points, a distance r from a given point, grows like r squared. In fact, in four-dimensional space, it grows like r cubed. And so, in general, if you've got d-dimensional space, the number of points which are at a distance r from a given point is going to grow like r to the d minus 1, r to the power of d minus 1. And so, on a graph structure, one can find out how many vertices there are within d, within a distance d from a given point. And then one can use this kind of definition to associate the space with a kind of dimension. So effectively one asks, how fast does the number of vertices a given distance from a vertex grow with the radius? So you're really looking at kind of like the number of vertices in the shell of a generalized sphere about a point. Now, in all the cases I've talked about so far, in fact, in most cases of these systems, the number of vertices grows. The dimension of a network, according to this node shell dimension, and one can see papers by Thomas R. Bolognesi on causal networks for a rigorous definition of this. But anyway, in all of the networks I've talked about so far, the node shell dimension is well defined, unless the systems go fixed. The node shell dimension is well defined, and it tends to be between 2 and 3, or maybe between 1 and 3. So these systems tend to have quite low node shell dimensions. And so they correspond to something like 1, 2, or 3-dimensional space, or something in between. But in fact, one can see other systems like this one here that I'm showing. And this is really quite interesting. Firstly, have a look at the rules. They're kind of generalized. We've got these kind of operations here where we're replacing vertices, we're replacing triangles with squares. So, excuse me. Oh, sneezing. Okay. Um, so we've got these kind of operations where we're replacing triangles with squares. These actually correspond to exchange style operations. So when we look at networks like this, again evolving from the cube, we find more complex, we find interesting kinds of networks like this one, which actually corresponds to hyperbolic space. In this network here, the number of vertices grows a given distance from a vertex grows exponentially with the radius of the r-ball. So these systems are hyperbolic. In fact, one can kind of prove it. So it's interesting that one finds all different varieties of space within these kinds of systems. Okay, so I think that pretty much concludes my discussion. Maybe just show you one more thing. Where are we now? There we are. There we are. I'm just trying to find the pictures. Okay. So, what about the relevance of these systems to the real world? Well, here are some rules, and here are some objects these rules produce, which have some similarity to real world objects, okay? So now I'm using a different colour scheme. I've got a white background, and now the writer vertex is illustrated as black, okay? So again, we're evolving from the cube. This system here produces things that look kind of like a mushroom if you do this kind of spring embedding drawing. And this harkens back to the point which I made before about how some of these systems with repetitive growth can produce structures which look kind of like plants or mushrooms in this case. Okay. Here's a network which this rule produces something that looks a little bit like a turtle shell. If one evolves it from a cube, and then just doing a spring embedding, one sees that the network looks quite a lot like a turtle shell. This network has repetitive growth, and it makes something that looks quite similar to a caterpillar. This rule produces this kind of thing, which I think has some kind of similarity to telescopium seashells. And this kind of network has some kind of vague similarity to a brain. And this one produces something that looks quite similar to a necklace. So there we are. We can produce networks which look a lot like many different kinds of real-world objects, and that's kind of an interesting thing to be able to do. Now, in every single case which I've discussed so far, our initial condition was the cube. So one thing you might be wondering about is what happens when you evolve these kind of systems from something other than a cube? What do you get? Well, one thing you can do, if you want to be systematic about it, is you can think about cylinders. Okay? So a cylinder is where you get two polygons, and then you put, so imagine two polygons, one above the other, and then put some kinds of sticks downwards connecting corresponding corners of the polygons. You know, triangular prism, cube, pentagonal prism, hexagonal prisms, etc. The thing is that if you have prisms where the end polygonal faces have even numbers of vertices, you can do a tape colouring of those kind of prisms quite naturally. I mean, you can just colour the polygons on the end red, blue in an alternating fashion, and you can just colour the kind of vertical sticks green, and that's quite a natural way to get polygons to get prisms with these kind of red, blue, green edge colorings. And so that gives you kind of natural space of initial conditions to evolve these rules from. And so what do you see when you evolve these rules from different initial conditions? Well, I did some experiments a few months ago, and what I found was that there's really quite interesting things that can happen under certain rules. Certain rules seem to have incredible sensitivity to the initial conditions, so that, for example, if you evolve a system from a cylinder based on a 10-gon, you'll see that the system expands to, say, 1,000 vertices and then becomes fixed. If you evolve a thing from a 12-gon, maybe it just grows forever. And if you evolve it from a 14-gon, then maybe it becomes fixed after 500 time steps, etc. So some of these systems really do have very complicated dependencies on the initial conditions. And that's kind of interesting because it means that, in a way, you can kind of program these systems. I mean, if you're interested in doing some kind of non-conventional computing, you can think about things like initializing these networks from different systems to perform different kinds of computations. Okay, so time to wrap up. Basically, the study of these systems is still in its early stages. I think they're pretty interesting. I think that hopefully these kind of things can find some kind of real-world applications. I mean, the idea of having networks which rewire themselves and kind of store information in complicated ways certainly reminds one of things like brains or databases. And also, these systems are kind of physically realizable. I mean, one could make a kind of robot or something which pulls itself along chains, or some kind of weaving or sewing mechanism which is based upon these systems. And so who knows, maybe something similar to these things could actually be used to produce materials in the world. And so, I think these things are fairly interesting, and I intend to keep studying them.